Hey guys, welcome to Safi Mixed. In this video, I will let you know about Pythagorean triple and will construct some equations that would allow us to find different set of Pythagorean triples. So we know from Pythagorean theorem that a right angle triangle with side lengths ABC satisfied the equation a squared plus b squared plus c squared. Now, the set of any three numbers that satisfy this equation is called Pythagorean triple. For example, two well-known Pythagorean triples that we can express as number one is 3, 4, 5, and the second one 5, 12, and 13. These sets of numbers are Pythagorean triple because each of them satisfied this one equation. So let us try to show that that this one satisfied the equation. So I can write a squared plus b squared, and now I put the value of a and b, which is 3 and 4, to write it 3 square plus 4 square, and I can write 3 square as 9, 4 square as 16. That allows me to write this thing to sum them up as 25, and we know 25 is the square of 5, so 5 square means this is equal to c squared. So we see, starting with the square of these two numbers, we end up with the square of the third number. So this in fact is the Pythagorean triple. Similarly, you can try to verify that this is definitely a Pythagorean triple. Now the question is, are these two sets the only Pythagorean triple? The answer is no. There are several Pythagorean triples, and we want to construct a relation to find very large number of Pythagorean triple. For that, we need to look into a particular pattern in these two pairs. We see that the last number is one more than the second last number. For example, 5 is 1 more than 4, and the same is true over here. 13 is 1 more than 12. That means we can write C as 1 more than B. That is, I can write C is equal to B plus 1. And writing that value, I can put this equation into the form a square plus b square equals b plus 1 square, where I'm writing for c equals b plus 1. From this, I can find a square equals b plus 1 square minus b square. That is, I'm taking this term to this side, that becomes minus. And now if I open this square, I get b squared plus 1 plus 2b minus b squared, and I can cancel this b squared with this b squared. That allows me to write a squared equals 1 plus 2b. I call this equation 1. Now for b being an integer, 2b plus 1 is always an odd number. This means that a squared is in fact equal to an odd number. And from the properties of odd numbers, we know that the square of an odd number is always equal to an odd number. That means a is also an odd number. That's why the square of a is an odd number. So from the property of odd numbers, I can write a in the form of 2n plus 1, where n is an integer. So I call this equation 2. Now, in terms of n, we can define b as well from equation 1, because from equation 1 I can write 2b equals a squared minus 1. I'm taking this one to this side of the equation, so that will become minus 1, and from this I can write b equals a squared minus 1 divided by 2. Now, putting the value of a from equation 2 at this position, I can write b in the form of 2n plus 1 square minus 1 divided by 2. So if I want to further simplify this at this position, I can write b is equal to 4n squared plus 1 plus 4n minus 1. That is, I open first the square and then subtract minus 1 and write the 2 at its own place. I can cancel this one with this one, so I'm left with two terms in the numerator, and from the two terms I can take 2 common, because here is 4, here is 4, and that common 2 I can cancel with the 2 in denominator. This allows me to write b equals 2n squared plus 2 times n. I call this equation 3. Now, since by definition and from the pattern of this number, we said c equal to b plus 1. Therefore, in terms of this value, I can write c equals b plus 1, and putting the value of b from equation 3, I construct this one equation 2n squared plus 2n plus 1, and I call this equation 4. That means equation 2, equation 3, and equation 4 together define a large number of Pythagorean triples in terms of integer n. For example, for n is equal to 1, here I can write 2 times 1 plus 1, this would give me 3, and this would give me 2, and this would give me 2, so 2 plus 2 is 4, and 4 plus 1 is 5, so I get 3, 4, 5, a Pythagorean triple, this one. And for n is equal to 2, I can put the value. This would become 2 times 2 is 4, and this would give me 5, and this would give me 12, and then 12 plus 1 is equal to 13. So it is this one Pythagorean triple. Similarly, substituting the value for n is equal to 3 in equation 2 would give me 7, and n is equal to 3 in equation 3 would give me 24, and then 24 plus 1 is 25. Okay, that means with the help of equation 2, 3, and 4, we can find a very large number of Pythagorean triples. But the question is, uh, do equation 2, 3, and 4 catch all the possible Pythagorean triple? The answer is no, because we have another Pythagorean triple in the form of 8, 15, and 17. Let us first verify that this is exactly a Pythagorean triple. So I want to put these values in this equation, and I start from 8 squared plus 15 squared. So 8 squared is 64 and 15 squared is 225. Summing them together gives me 289, and you can easily verify that 289 equals the square of 17. That means this defines a Pythagorean triple, or this set of numbers defines a Pythagorean triple, but we cannot obtain this set of numbers from equation 2, 3, and 4, because for no value of n, this gave us 8. 8 is an even number, and equation 2 always gives odd numbers. So at the end, let me remind that any set of numbers that satisfy Pythagorean equation or Pythagorean theorem is called Pythagorean triple, and we can find a large number of Pythagorean triples from equation 2, 3, and 4, but these equations do not give all the possible Pythagorean triple, like we are unable to obtain this one Pythagorean triple from equation 2, 3, and 4. At the end, thanks for watching.